Back in 2017, some researchers at Google dropped a paper with a kind of poetic title, Attention is All You Need. But this thing wasn't just a small improvement. Nope. It gave us a totally new blueprint for AI called the Transformer. So let's dive in and see how this one paper completely changed the game for artificial intelligence.
It feels like AI took this giant leap almost overnight, right? All of a sudden, we have models that can translate languages in a blink, write actual code, create incredible art. But have you ever stopped and asked, why? Why now? What was the Big Bang moment that unleashed all this power? Well, the answer comes down to breaking one fundamental speed limit.
Okay, so before 2017, the world of language AI was pretty much run by one type of model, the recurrent neural network, or RNN. And look, they were clever for their time, but they had this built-in problem, a fundamental bottleneck that was holding back, well, everything. I want you to imagine reading a sentence, but you can only see one word at a time through a tiny pinhole. That's kind of how an RNN worked. It reads the first word, thinks about it, then moves to the second word, thinks about that one in the context of the first, and so on and so on. It's logical, sure, but it's painfully slow. You literally cannot process word number 10 until you are completely done with word number 9. It's a traffic jam, and it means you can't really use parallel processing to speed things up. You just have to wait.
And this is where the Transformer just flips the whole table. Instead of that one word at a time slog, it asks a different question. What if the model could just see all the words all at once? It replaces that slow, sequential line with a massively parallel process. It's the difference between reading a book one word at a time versus just opening your eyes and seeing the whole page instantly. This was the shift. This is what changed everything.
And you don't have to take my word for it. This little table from the paper says it all. Look at the row for recurrent. See that ON? That's just a fancy way of saying the number of steps grows with the length of the sentence. More words means more time. It's a straight line up. But now look at self-attention, O1. That means it's a flat line. It doesn't matter if the sentence has 10 words or 1,000. The model can connect any two words in basically a single computational step. This wasn't an improvement. This was like breaking the known laws of AI physics.
You know, the researchers behind this paper weren't just trying to make things a little bit faster. They were proposing we throw out the entire rulebook. They saw that sequential bottleneck not as a problem to be optimized, but as a wall that needed to be completely demolished.
This quote right here from the paper's abstract was basically a declaration of war on the old way of doing things. For years, the common wisdom was that to understand a sequence, you needed recurrence. It just made sense. But these authors came along and said, nope, you don't need it. They built a model based solely on something called attention, completely getting rid of the one word at a time processing that had defined the field for years. This was a really big deal.
So okay, if you throw out recurrence, what's left? What is this attention thing that's so powerful it can replace the entire foundation of language AI?
The big idea is called self-attention. And what it does is it lets the model look at one word, and then, by looking at all the other words in the sentence at the exact same time, it figures out which ones are most important for understanding that first word's meaning. So take the sentence, the car stalled because it ran out of gas. Self-attention is how the model instantly knows that the word it is talking about the car, not the gas. It sees all the connections at once.
So how does it pull this off? Well, the basic building block is this thing called scaled dot product attention. But the real magic happens when you run a bunch of these in parallel. The paper calls it multi-head attention. Think of it like this. You don't have just one person reading this sentence. You have a whole committee of specialists reading it at the same time. One head might be a grammar expert. Another is looking for how pronouns connect to nouns. A third is tracking something else entirely. They all work at once, in parallel, which gives the model this incredibly deep, layered understanding of the sentence in a flash.
All right, so you've got these super powerful, multi-head attention blocks. What do you build with them? Well, the authors put them together to create a brand new architecture. Let's take a quick look at the blueprint that started it all.
And here it is, the full Transformer architecture. Now, I know this looks like a circuit diagram from a spaceship, but don't worry, the main idea is pretty simple. See the two big columns? The one on the left is the encoder. Its job is to read and understand the input, like a sentence in English. The column on the right is the decoder. Its job is to generate the output, like the same sentence in French. And what's the most important part? Both of them are just stacks of those multi-head attention blocks we were just talking about. Attention is literally the engine driving this whole machine.
So the model is built out of these repeating units. The original paper used a stack of 6 encoders and 6 decoders, each one with our multi-head attention mechanism inside. But that brings up a really good question, right? If the model sees all the words at once, how does it know what order they're in? Well, they used a super clever trick called positional encodings. It's basically like adding a little bit of information to each word that says, hey, I'm word number 1 or I'm word number 5. That way the model gets a sense of position without having to go one by one.
Okay, so the architecture was elegant, the theory was brilliant, but the billion-dollar question was, did it actually work? Was it any good? The answer was a resounding yes, and the proof was in its groundbreaking results.
This was the first jaw on the floor moment. On a standard translation benchmark, the Transformer didn't just beat the best models in the world, it crushed them. The score is measured in something called blue points, and in this field, an improvement of, like, 0.1 is a big deal. The Transformer improved the state-of-the-art by over 2.0 points. That's not a step forward, that is a giant leap.
And then came the knockout punch. It achieved this incredible new state-of-the-art performance while using, in some cases, less than a quarter of the computing power to train. So think about that. By demolishing that sequential bottleneck, they made a model that was not only way better, but also massively more efficient. The data really lays it all out. You don't have to be a data scientist to read this table. Just look at the bold numbers. In both English to German and English to French translation, the Transformer just blows past the previous best models. It even beat these complex systems that were basically a bunch of different models cobbled together. The Transformer, as a single, elegant architecture, was just better. So what's the big takeaway here? It's actually kind of profound. This whole journey started as a quest for more speed and efficiency. But by solving that problem, they accidentally unlocked a whole new level of performance. By letting the model see the entire context of a sentence at once, self-attention allowed it to understand these deep relationships and nuances that the old models just couldn't grasp. It turned out that being able to see the whole picture at once wasn't just faster, it was smarter. The legacy of this one paper is pretty much the entire AI world we live in today. Every single large language model you've heard of, ChatGPT, Gemini, you name it, has a transformer at its heart. By cracking that parallelization problem, this architecture paved the way for models to be trained on unbelievable amounts of data. Which kind of leaves us with one final thought. This paper showed us what happens when a model can see a whole sentence at once. What happens when it can see the whole book or the whole library?